Imagine gazing up at the night sky, feeling the weight of all those twinkling stars and distant planets, knowing that despite centuries of human curiosity, our own solar system still holds secrets that defy explanation. We've sent probes to the edge of interstellar space, mapped the surfaces of alien worlds, and yet the more we learn, the more questions arise: strange phenomena, unexplained anomalies, and cosmic puzzles that leave even the brightest scientists scratching their heads. This isn't just about what we know, it's about the thrilling gaps in our understanding, the mysteries that keep us searching. Take Jupiter's Great Red Spot, for example, a storm so colossal it could swallow Earth whole, raging for hundreds of years. But here's the thing, no one really knows why it's still there or what fuels its fury. Or consider the eerie hexagon hovering over Saturn's North Pole, a geometric spectacle unlike anything else in nature. How does something so precise exist in the chaos of space? These aren't just curiosities, they're clues to deeper, unanswered questions about the forces shaping our cosmic neighborhood. And they're just the beginning. Today, we're diving into 30 of the most baffling unsolved mysteries of the solar system, enigmas that challenge everything we think we know. From vanishing spacecraft to whispers of hidden planets lurking in the darkness, each one is a reminder that the universe loves to keep us guessing, so buckle up. Because by the end of this journey, you'll see the solar system not as a static map of planets and moons, but as a living, evolving puzzle, one where every discovery pulls back a curtain to reveal even grander questions waiting in the shadows. Ready to explore? Let's begin. Think about the hottest place you've ever been. Now imagine standing on Mercury, where daytime temperatures soar high enough to melt lead. Yet against all logic, this blistering world holds pockets of ice hiding in permanent shadows at its poles. How does ice survive just 48 million miles from the sun? Mercury shouldn't have water at all, let alone frozen deposits tucked inside craters. Scientists first spotted these glimmers of ice using radar in the early 1990s, and later missions like NASA Messenger spacecraft confirmed it. But the real mystery isn't just that the ice exists, it's how it got there in the first place. One leading theory suggests comets, those cosmic snowballs, might be the delivery system. Over billions of years, comets crashing into Mercury could have left behind water that settled in polar craters, deep, sunless pits where temperatures plunge to hundreds of degrees below freezing. No sunlight ever reaches these shadowy chambers, creating natural freezers that trap water ice for eons. But here's the twist, some of this ice appears unusually pure, almost untouched by Mercury's dusty surface. If comets brought it, why isn't it mixed with more debris? That's where things get even stranger. Another idea proposes Mercury might have its own secret water source. Hydrogen from the solar wind could react with oxygen in the planet's rocks, slowly creating water molecules that migrate to the poles over time, or perhaps buried reservoirs, remnants of ancient volcanic activity, still leak water vapor into the cold traps. What's wild is that this seemingly dead planet might still be geologically active, with hidden processes we're only beginning to unravel. The implications go beyond Mercury. If a scorching world like this can hoard ice, what does that mean for other seemingly inhospitable places in the solar system? Every new discovery peels back another layer, showing us just how little we truly understand about the delicate dance of water and heat in the cosmos. Mercury's icy secret isn't just a puzzle, it's a clue, whispering that even in the most extreme environments, nature finds a way to surprise us. Venus was once considered Earth's twin, a rocky world of similar size and composition, wrapped in clouds that might have even hinted at oceans long ago. But today it's a nightmare landscape, with surface temperatures hot enough to melt lead, crushing atmospheric pressure 90 times heavier than Earth's, and skies raining sulfuric acid. So what went wrong? How did a planet so similar to ours become a cautionary tale of cosmic extremes? The answer lies in something called the runaway greenhouse effect. a chain reaction so powerful it transformed Venus into the solar system's hottest planet, even hotter than Mercury, despite being nearly twice as far from the Sun. Scientists believe Venus started with water, perhaps even vast oceans, but as the young Sun grew brighter, the planet's fate took a dark turn. Heat trapped by carbon dioxide in the atmosphere began evaporating its water, releasing more greenhouse gases in a vicious cycle. Water vapor, itself a potent greenhouse gas, accelerated the warming, baking the surface until the oceans boiled away entirely, with no water left to absorb carbon dioxide. Through processes like Earth's rock weathering, the gas built up unchecked. Today, Venus's atmosphere is 96% carbon dioxide, a suffocating blanket that locks in heat with terrifying efficiency. What's especially chilling is how quickly this might have happened. Some models suggest Venus could have spiraled into its hellish state in as little as 600 million years, a blink of an eye in cosmic terms, and that raises an unsettling question: could Earth one day follow the same path? The parallels are hard to ignore. Human activity has already increased atmospheric carbon dioxide levels by 50% since the Industrial Revolution, pushing our climate into uncharted territory. While Earth has stabilizing mechanisms Venus lacked, like active plate tectonics that recycle carbon over millennia, the risk of tipping points remains. Venus stands as a stark warning, a reminder that even small changes can cascade into irreversible catastrophe, but it also holds clues to our own survival. Studying its atmosphere helps scientists refine climate models, revealing how thin the line between habitable and hostile truly is. The more we learn about Venus's past, the better we understand Earth's future and the urgent need to protect the delicate balance that keeps our world alive. Earth's moon seems like a quiet, unchanging neighbor, a lifeless rock pockmarked by ancient craters, but beneath that silent surface lies a puzzle that's baffled scientists for decades, evidence that this small, seemingly inert world once had its own magnetic field, something only planets with molten, churning cores should possess. Today, the moon has no global magnetic shield, yet samples brought back by Apollo astronauts contain minerals that were clearly magnetized billions of years ago. How could something so small, roughly a quarter of Earth's size, generate a magnetic dynamo strong enough to leave traces in its rocks? The answer might rewrite what we know about planetary formation. One leading theory points to a dramatic early history. Shortly after its formation, the moon may have had a molten core, kept liquid by intense heat left over from its violent birth, likely a collision between Earth and a Mars-sized object. As this core churned, it could have created a magnetic field, much like Earth's does today, but here's the catch: small bodies lose heat rapidly. Without a massive mantle to insulate it, the moon's core should have cooled and solidified within a few hundred million years, snuffing out its magnetic shield. Yet the Apollo samples tell a different story. Some of these magnetized rocks date back to around 3.5 billion years ago, far later than expected, suggesting the dynamo somehow persisted. Alternative explanations add even more intrigue. Some researchers propose that massive asteroid impacts could have temporarily stirred the moon's core, reigniting its magnetic field in short bursts. Others speculate that the moon's orbit once brought it much closer to Earth, where tidal forces stretched and heated its interior like dough in a cosmic oven. There's even a wilder idea. What if the moon's crust itself played a role? Early in its history, radioactive elements concentrated near the surface might have generated enough heat to keep subsurface layers molten far longer than models predict. The implications stretch far beyond lunar science. If small, rocky worlds like the moon can sustain magnetic fields longer than thought, it changes how we search for habitable exoplanets. Magnetic shields protect atmospheres from being stripped by solar winds, meaning moons around distant gas giants might harbor conditions for life. Every rock brought back from the moon carries echoes of an ancient invisible force, one we're only beginning to decode. And until we solve it, the Moon's magnetic past remains a ghostly reminder of how little we truly know about the worlds orbiting beside us. Mars has always been the planet of unanswered questions, but few mysteries are as tantalizing or as frustrating as the sporadic bursts of methane detected in its thin atmosphere. This simple molecule, made of just one carbon atom and 4 hydrogen atoms, shouldn't linger long on Mars. Solar radiation and chemical reactions should break it apart within a few hundred years. So why do our instruments keep picking it up in sudden, unpredictable spikes? The implications are staggering. On Earth, 95% of methane comes from living organisms. Could the same be true on Mars, or is some unknown geological process playing tricks on us? NASA Curiosity rover has been sniffing out these methane whispers since it landed in Gale Crater in 2012. Some of its readings show background levels barely above 1 part per billion, but then without warning, the numbers suddenly jump tenfold or more, lasting only hours before vanishing. What's bizarre is that Europe's ExoMars Trace gas orbiter, circling the planet from above, often detects nothing at all during these same spikes. At first glance, this seems impossible. How can one instrument smell methane while another, supposedly more sensitive one, misses it entirely? One theory suggests the methane might be trapped underground, escaping through cracks or porous rock. In brief, localized puffs too small for orbiters to spot. Curiosity, sitting right on the surface, could be catching whiffs of these micro-leaks before the gas disperses into the atmosphere. Another possibility. The orbiter's measurements happen at different times of day. Maybe sunlight, or atmospheric chemistry, is destroying the methane before it can rise high enough to be seen from space. Then there's the life question. Certain microbes on Earth thrive deep underground without oxygen, producing methane as a byproduct. If similar organisms exist beneath Mars's frozen surface, their burps could explain the sporadic detections. But before we jump to aliens, consider this. Methane can also form when water reacts with certain minerals, like olivine, in a process called serpentinization. With evidence of ancient water all over Mars, this geologic explanation is just as plausible. The real puzzle isn't just where the methane comes from, it's why it behaves so unpredictably. On Earth, methane follows patterns tied to seasons or temperature. On Mars, it's a ghost, appearing and disappearing without rhyme or reason. Solving this riddle might require new tools, like drills capable of digging deeper or sensors that map gas flows in real time. Until then, every whiff of methane keeps us guessing. Is Mars hiding a secret biosphere, or are we watching geology rewrite its own rules? Either way, the answer could redefine our place in the cosmos. In the vast windswept plains of Mars's Cydonia region, a single landform captured humanity's imagination like nothing else. A mile-long mesa that, when photographed by NASA Viking 1 orbiter in 1976, appeared to stare back at us with eerily human features. The so-called face on Mars became an instant sensation, igniting feverish speculation about ancient alien civilizations carving monuments into the red planet's surface. Conspiracy theories exploded, claiming NASA was hiding the truth, but here's the twist: it was never a face at all. Years later, high-resolution images from missions like Mars Global Surveyor revealed the truth. The face was nothing more than a trick of light and shadow, an ordinary rock formation with no symmetrical features. Yet even after debunking, the fascination persisted. Why? Because this cosmic optical illusion taps into something primal in the human brain: pareidolia, our hardwired tendency to see familiar patterns, faces, animals, even religious figures in random shapes. It's why we spot bunnies in clouds or the man in the moon staring down at Earth. There's a deeper irony here. While the face on Mars was a false alarm, the same phenomenon has led to genuine scientific discoveries. When NASA's Spirit rover photographed a rock formation nicknamed the Martian Bigfoot in 2007, the internet lit up with claims of a humanoid figure. Again, closer inspection showed just an oddly shaped rock, But pareidolia isn't just about mistakes, it's a survival mechanism. Early humans who quickly spotted faces in the bushes, real or not, were more likely to avoid predators. Today, that same instinct drives everything from Rorschach tests to AI algorithms trained to recognize patterns. Mars, with its barren landscapes and shifting shadows, is a perfect canvas for these illusions. From the Martian spoon, photographed by Curiosity, to the alien thigh bone that turned out to be eroded rock, each new discovery follows the same cycle: excitement, scrutiny, debunking. Yet we keep looking. Maybe it's hope, a desire to find companionship in the cosmos, or maybe it's a reminder that even in the age of high-resolution cameras and robotic explorers, the universe still knows how to play tricks on us. The real mystery isn't about aliens, it's about why we're so desperate to see them in the first place. Phobos shouldn't exist, at least not where it is. Mars's larger moon orbits so close to the planet that it defies conventional wisdom, just 300 miles above the surface, closer than any other moon to its parent body in the entire solar system. From the Martian surface, Phobos appears 3 times larger than Earth's full moon, racing across the sky so fast it rises and sets twice a day. But here's the real shocker: it's in a death spiral. Every century, tidal forces drag Phobos 6 feet closer to Mars, and in about 50 million years, it will either crash into the planet or be torn apart into a ring of debris. Why is this oddball moon on such a doomed trajectory? Some scientists think the answer lies in its origin story, and a few even wonder if it's not a moon at all. Most natural satellites, like Earth's moon, form in one of 2 ways. Either they coalesce from leftover material around a planet during its formation, or they're captured asteroids drifting too close to a planet's gravity. Phobos doesn't fit neatly into either category. Its orbit is too circular and aligned with Mars's equator for a typical captured object, yet its composition, dark, porous, and carbon-rich, matches certain asteroids in the outer solar system. This mismatch led to a radical theory in the mid-20th century that Phobos might be hollow. The idea came from Soviet astrophysicist Iosif Hitlovsky, who studied Phobos's odd acceleration and concluded its density was implausibly low, so low, in fact, that it could be an artificial structure. His controversial suggestion that an ancient Martian civilization facing extinction built Phobos as a space station or ark, while later measurements showed the moon isn't hollow. Its density is still suspiciously light, about 1.8 grams per cubic centimeter, less than half that of Earth's moon. Some researchers argue this points to a rubble pile structure, held together weakly by gravity, while others propose it's a captured asteroid wrapped in a thick layer of loose dust. The plot thickens when you examine its surface. Phobos is scarred by a network of mysterious grooves, long, parallel trenches that look like stretch marks. One explanation suggests these were carved by debris ejected from massive meteor strikes on Mars, like Stickney crater, which nearly shattered Phobos billions of years ago. But another fringe hypothesis: the grooves are remnants of artificial supports or infrastructure beneath a crumbling outer shell. For now, the debate remains unresolved. Japan's upcoming Martian moons exploration mission aims to bring back samples from Phobos by 2029, which could finally settle the question of its origin. Whether it's a captured asteroid, a shattered relic of a larger moon, or something even stranger, Phobos' slow dance toward destruction reminds us that even the seemingly permanent features of our solar system are fleeting. And if there's one lesson its erratic orbit teaches us, it's that the universe has a flair for the dramatic, leaving us to puzzle over the clues long after the curtain falls. Jupiter should be the textbook example of a gas giant, a massive ball of hydrogen and helium with a dense, rocky core buried deep beneath its swirling clouds. That's how planetary formation models say it should work. But when NASA Juno spacecraft began peering beneath Jupiter's turbulent surface in 2016, it uncovered something shocking: the planet's core isn't solid and compact. Instead, it's fuzzy, diluted, almost as if someone took a billion Earth-sized rocks and blended them into the surrounding metallic hydrogen soup. This isn't just a curiosity, it's a direct challenge to everything we thought we knew about how planets are born. One leading theory points to a cataclysmic past. Imagine Jupiter newly formed, its core still molten and vulnerable. Then, another protoplanet, perhaps 10 times Earth's mass, smashes into it head-on. The collision wouldn't just crack Jupiter's core, it would scatter it, mixing heavy elements like iron and silicon into the surrounding layers like cream stirred into coffee. Computer simulations show such an impact could explain Juno's measurements, but the timing is tight. For the debris to stay suspended rather than sinking back to the center, the crash had to happen early, while Jupiter was still young and puffy from its formation heat. Yet there's another even wilder possibility. Maybe Jupiter never had a traditional core to begin with. Some astrophysicists argue gas giants could form through a process called disk instability, where a swirling cloud of gas and dust collapses directly into a planet without first building a rocky heart. If true, Jupiter's core might just be a region where heavier elements naturally settled over time, more like a gradient than a distinct layer. The problem. This contradicts the prevailing core accretion model, which says all gas giants start with a solid seed massive enough to pull in surrounding gas, and then there's the exotic matter angle. Deep inside Jupiter, pressures exceed those at Earth's core by 40 million times, squeezing hydrogen into a bizarre metallic state that conducts electricity like copper. Could unknown physics at these extremes be disguising the core's true nature? Experiments with diamond anvils here on Earth can't yet replicate conditions that intense, leaving us to guess how matter behaves in such alien environments. Jupiter's missing core isn't just a puzzle for planetary scientists, it's a window into the chaos of the early solar system. Every probe that dips beneath its clouds reveals a world stranger than fiction, where the rules we take for granted don't always apply. Whether shattered by violence, born without a center, or hiding secrets we can't yet fathom, Jupiter reminds us that even the grandest theories must bend when faced with the messy reality of the cosmos. Jupiter's great red spot isn't just a storm, it's a cosmic endurance champion. This swirling vortex, wider than Earth itself, has churned non-stop for at least 150 years, with some historical records suggesting it might have been raging since the 1600s. That's older than the United States, older than the steam engine. How does a hurricane, even a planetary-scale one, sustain itself for centuries without running out of steam? The answer lies in the chaotic dance of Jupiter's atmosphere, where the rules of weather defy everything we know about Earth. Unlike terrestrial storms, which rely on warm ocean water for energy, the Great Red Spot thrives on sheer momentum. Jupiter has no solid surface to disrupt its flow, just layers of gas, stretching tens of thousands of miles deep. The storm acts like a spinning top, caught between opposing jet streams that funnel energy into it like an endless battery. One stream races eastward at over 200 miles per hour, while another hurtles westward, sandwiching the spot in a perpetual tug-of-war that keeps it rotating counterclockwise. But here's the real kicker. Instead of weakening over time, the storm appears to be feeding off its own chaos, drawing power from smaller eddies that collide and merge into its crimson embrace. Yet even this doesn't fully explain its staying power. On Earth, hurricanes dissipate within days or weeks when they hit land or cool waters. Jupiter's storm persists because it's not just a temporary disturbance, it's a self-sustaining system, a kind of atmospheric machine. Recent data from NASA Juno mission revealed something startling. The Great Red Spot plunges over 200 miles beneath Jupiter's cloud tops, far deeper than anyone suspected. This depth suggests the storm might be anchored by heat rising from the planet's interior, creating a feedback loop where warmth fuels winds, which in turn draw up more heat. It's a cosmic perpetual motion engine with no brakes in sight, but nothing lasts forever. Observations over the past few decades show the spot is shrinking. Once large enough to swallow 3 Earths, it's now barely wider than one. Some researchers believe it could vanish within our lifetimes, while others argue it might simply be condensing, growing taller as it narrows. Even if it disappears, new storms will likely take its place. Jupiter's atmosphere is a factory of tempests, with cyclones and anticyclones constantly forming, merging, and fading like characters in an epic celestial drama. The Great Red Spot's mystery isn't just about longevity, it's a window into the invisible forces shaping gas giants across the universe. If we can unravel how this ancient storm defies time, we might finally understand why some planetary weather lasts millennia, while ours fades in days. For now, it remains a blazing question mark in Jupiter's skies, a reminder that even the mightiest phenomena are just fleeting guests in the grand theater of the cosmos. Beneath Europa's cracked, icy shell lies one of the most promising and enigmatic environments in our solar system, a vast global ocean that could hold more liquid water than all of Earth's seas combined. This frozen moon of Jupiter, roughly the size of our own moon, shouldn't have the conditions for liquid water, not at surface temperatures plunging to minus 260 degrees Fahrenheit. Yet the evidence is undeniable. Europa's surface is a fractured labyrinth of ridges and grooves, like a jigsaw puzzle of ice flows constantly shifting and refreezing. These scars tell the story of a subsurface ocean flexing and churning beneath the ice, tugged by Jupiter's immense gravitational pull. The first clues came from Voyager and Galileo spacecraft images, revealing a surface too young and active to belong to a dead world. Europa has almost no craters, a sign its icy crust is continually renewed, erasing impact scars over time. Then there are the plumes, towering geysers of water vapor erupting from fissures near the Moon's south pole, captured by the Hubble Space Telescope in 2012 and again in 2016. These aren't just icy vapor spectrometers detected salts and organic molecules mixed in, the kind of chemistry that, on Earth, supports entire ecosystems around deep-sea hydrothermal vents. But what keeps this ocean liquid so far from the Sun? The answer lies in tidal heating. As Europa orbits Jupiter, the gas giant's gravity stretches and squeezes the Moon's interior, generating friction and heat. This same process powers the volcanoes of Io, Jupiter's fiery neighbor. On Europa, that energy melts ice instead of rock, creating a dark, salty ocean sealed under an ice shell up to 15 miles thick. And where there's heat, water, and chemistry, there's potential for life. NASA's upcoming Europa Clipper mission, launching as early as 2024, aims to crack this mystery wide open. Armed with ice-penetrating radar and sensors to analyze plume material, it will map the ocean's depth, salinity, and even its currents. Meanwhile, the European Space Agency's JUICE probe will study Europa alongside Ganymede and Callisto, hunting for clues in their contrasting geologies. The ultimate goal, to pinpoint landing sites for a future mission that might drill, or melt, its way through the ice to directly sample the ocean itself. Imagine what we might find. On Earth, life thrives in the most extreme places: volcanic vents, Antarctic lakes buried under miles of ice, even radioactive reactor pools. Europa's ocean, shielded from radiation and rich in energy from tidal forces and possible hydrothermal vents, could harbor similar extremophiles, or perhaps something even stranger, evolved in isolation over billions of years. The discovery of life, or even its building blocks on Europa, wouldn't just rewrite textbooks, it would redefine humanity's place in the universe, proving we're not alone in the cosmic dark. Until then, Europa remains a tantalizing enigma, its secrets locked beneath ice and shadow, waiting to be uncovered. Saturn's North Pole isn't just another swirl of storms, it's a geometric masterpiece, a near-perfect hexagon stretching 20,000 miles across, with each side longer than Earth's diameter. This six-sided vortex, first spotted by Voyager in the 1980s and later studied in breathtaking detail by Cassini, defies every expectation of how planetary weather should behave. Hurricanes on Earth are circular, Jupiter's great red spot is oval, but Saturn's hexagon, it's a polygon sculpted from gas with razor-sharp edges that have persisted for at least 40 years, possibly much longer. How does a storm or whatever this is maintain such precise angles in a turbulent, roiling atmosphere? The answer might lie in the quirks of fluid dynamics. When liquids or gases rotate at different speeds, they can produce geometric patterns, something you can see in a simple lab experiment. Fill a cylindrical tank with water, spin it, and introduce a slower or faster current at the center, and you'll get shapes ranging from triangles to octagons. On Saturn, where winds scream at 320 miles per hour, the hexagon could be a standing wave, a stable pattern carved by competing jet streams at different latitudes. Think of it like a cosmic game of tug-of-war, where the planet's internal heat and rapid rotation lock the storm into this unnatural symmetry. But here's where things get weird. The hexagon isn't just a surface feature, it towers 60 miles high, a towering wall of clouds with layers of turbulence stacked like floors in a skyscraper. And it's not static. Cassini's infrared cameras revealed the storm changes color with Saturn's seasons, shifting from golden to blue as sunlight waxes and wanes over its 30-year orbit. Some researchers suspect this hexagon might actually be a colossal aurora, a side effect of Saturn's bizarre magnetic field. Unlike Earth's relatively straightforward north-south magnetosphere, Saturn's field is almost perfectly aligned with its axis of rotation, a unique trait that could funnel charged particles into a hexagonal pattern high in the atmosphere. Yet even these explanations don't fully account for the hexagon's persistence. Earth's weather systems dissolve in days, Jupiter's storms last centuries. But a geometric storm, that's something else entirely. One radical theory proposes that the hexagon is a shadow not of a physical object, but of a deeper, invisible structure. Saturn's interior might harbor layers of exotic matter, like metallic hydrogen, sloshing in ways that imprint these shapes onto the cloud tops above. It's as if the planet itself is a giant, slow-turning kaleidoscope, with the hexagon as its most dazzling reflection. The deeper we look, the more questions arise. Why 6 sides? Why not 5 or 8? Why does the hexagon remain locked in place while individual storms within it race around at breakneck speeds? Every answer peels back another layer of mystery, revealing just how little we understand about the hidden forces shaping gas giants. Saturn's hexagon isn't just a curiosity, it's a cosmic riddle, a reminder that even the most familiar planets still hold secrets waiting to be decoded. And until we send another probe to study it up close, this 6-sided enigma will keep spinning in the dark, daring us to unravel its secrets. Saturn's rings are the solar system's crown jewels, delicate bands of ice and dust that catch sunlight like a cosmic disco ball. But for all their beauty, these iconic features might be a fleeting spectacle. Recent discoveries suggest they could be vanishingly young by cosmic standards, perhaps forming as recently as the age of dinosaurs. That's a staggering claim when textbooks have long described them as primordial, dating back 4.5 billion years to Saturn's birth. So which is it? Are we witnessing an ancient relic of the solar system's infancy, or are Saturn's rings just a passing phase in the planet's life? The answer hinges on 2 pieces of evidence that seem to contradict each other until you dig deeper. First, there's the case for youth. When NASA Cassini probe dove between Saturn and its rings during its final orbits in 2017, it made an unexpected discovery. The rings are far lighter than anyone predicted. By measuring subtle gravitational tugs, scientists calculated their mass and realized they're 99% ice, with barely any rocky debris mixed in. That purity is a problem for the old ring theory. Over billions of years, space dust and micrometeoroids should have darkened the rings, turning them from brilliant white to dingy gray. The fact they're still pristine suggests they formed recently, perhaps when a passing comet or icy moon shattered under Saturn's gravity, but then there's the historical wild card. In 1610, Galileo became the first person to observe Saturn's rings through a telescope, though his crude instrument showed only strange ears on either side of the planet. Later astronomers like Christian Huygens in 1655 identified them as rings, but here's the twist: some 17th century sketches depict Saturn with unexplained bulges or appendages that don't match the rings as we know them today. Could these be clues that the rings were still forming, or even that earlier, fainter rings existed and dissolved? It's a tantalizing idea, though skeptics argue these discrepancies might just stem from blurry telescope views. The debate gets even messier when you consider ring dynamics. Saturn's gravity is constantly tugging material inward, creating rain, yes, literal rain of ice particles falling into the planet's atmosphere. Cassini detected enough of this ring rain to estimate the entire system might vanish in another 300 million years. If the rings were truly ancient, they should have evaporated eons ago unless replenished by some hidden source, like icy moon eruptions or captured cometary debris. Yet there's a counterpoint. Some parts of the rings, like the dense B ring, appear clumpy and structured in ways that suggest they've had time to settle into stable patterns over millions of years. And then there's Phoebe, Saturn's odd moon orbiting backward. Its dark surface, coated in material flung from the outer solar system, paints the leading face of its neighboring moon Iapetus black, evidence of a long-standing debris flow that should have also contaminated the rings if they were old. But they're spotless. The truth might lie somewhere in between. Perhaps Saturn has had multiple rings over its lifetime, ancient ones that eroded away, followed by new ones born from celestial collisions. Or maybe the current rings are indeed young, but they're just the latest chapter in a cyclical saga of destruction and rebirth. What's certain is this: we're lucky to live in an era when Saturn wears its jewels so boldly. A cosmic blink ago, they might not have existed at all, and in another, they'll be gone, leaving future astronomers to wonder how we ever saw them shimmering in the first place. Among Saturn's many moons, Hyperion stands out as one of the strangest, a misshapen lump of rock and ice that looks less like a celestial body and more like a cosmic sponge. This irregular moon, barely 250 miles across, is so porous that if you could squeeze it like a stress ball, it would compress to half its size without breaking. With a density barely half that of water, Hyperion is lighter than most known solids in the solar system. Toss it into an ocean, and it would bob like a cork. How did this bizarre world come to be? The answer might lie in a history of unimaginable violence, or a composition unlike anything else we've encountered. Hyperion's spongy texture is immediately obvious in close-up images from the Cassini spacecraft. Its surface is pockmarked with deep, sharp-edged craters, some lined with dark material that resembles dried sludge. These aren't your typical impact scars, they're cavernous pits, some stretching miles wide with barely any raised rims. That's because Hyperion isn't dense enough to withstand collisions the way most moons do. When asteroids strike, they don't just leave dents, they punch straight through, scattering debris and leaving behind a honeycomb of voids. Some scientists compare Hyperion's structure to a frozen foam, where empty spaces make up more than 40% of its volume. One theory suggests Hyperion is a survivor, a fragment of a much larger moon obliterated by a cataclysmic impact billions of years ago. Imagine a collision so powerful it shattered a world into rubble, with Hyperion as one of the few pieces that avoided being pulverized or swallowed by Saturn's gravity. This could explain its odd rotation too. Unlike most moons which spin predictably, Hyperion tumbles chaotically through space, its axis wobbling so wildly that its poles and equator trade places over time. It's the solar system's equivalent of a football thrown in a spiral gone wrong, a motion that hints at a traumatic past. But there's another possibility. Hyperion might be a captured object, a wanderer from the outer solar system rich in organic compounds. Those dark stains lining its craters, they're packed with hydrocarbons, complex molecules that could be the frozen remnants of ancient chemistry, similar to what we find on comets. If true, Hyperion could be a time capsule, preserving primordial ingredients from the era when planets were still forming. Its sponginess might then come from volatile ices, like methane or carbon dioxide, that slowly evaporated over eons, leaving behind empty pockets like a celestial Swiss cheese. The real puzzle isn't just Hyperion's past, though. It's why we haven't found more moons like it. Most porous bodies in the solar system, like comets, are tiny. Hyperion is enormous by comparison, yet it seems to be one of a kind. Is it a fluke, or are there other, frozen foam worlds lurking in the shadows of gas giants, waiting to be discovered? Until we send another mission to Saturn, this oddball moon will keep its secrets, a eerie reminder that even in a universe governed by physics, there's always room for the bizarre. Most planets in the solar system spin like tops, their axes tilted just a few degrees from upright Earth leans at a modest 23 degrees, Saturn at 27. Then there's Uranus. This ice giant rolls around the sun like a bowling ball knocked on its side, its axis tilted a jaw dropping 98 degrees. Seasons here aren't just mild shifts, they're extreme decades-long sieges of darkness and light, with each pole getting 42 straight years of sunlight, followed by 42 years of icy night. How did Uranus end up in this bizarre configuration? The leading theory points to a cataclysm so violent it reshaped the planet's destiny, but the details are far from settled. Picture the early solar system, a chaotic construction zone where planets jostled for space. Scientists suspect a protoplanet at least twice Earth's mass slammed into Uranus with such force that it sent the ice giant reeling. Computer simulations show this kind of impact wouldn't just knock Uranus sideways, it could also explain why the planet's interior is strangely cold compared to Neptune, its near twin. The collision might have blasted away much of Uranus's original heat, leaving its core oddly inert. Supporting this idea are the planet's moons and rings, which orbit in the same skewed plane, like a family of celestial objects all knocked sideways in unison. Yet not everyone is convinced. Some researchers argue a single impact wouldn't leave Uranus's magnetic field so misaligned it's tilted 60 degrees from the planet's already extreme rotational axis, creating a magnetosphere that corkscrews through space like a drunken spiral. Alternative theories suggest a series of smaller collisions, or even gravitational tugs from a now-vanished sibling planet during the solar system's turbulent youth. There's even a fringe idea that Uranus once had a massive moon whose orbit slowly dragged the planet sideways over eons, only for that moon to be ejected later, leaving no trace. But the wildest hypothesis, Uranus's tilt might not be the result of violence at all. Fluid dynamic models show that in a gas giant with layered interiors, slow internal currents could theoretically shift the planet's axis over time without any external trigger. Imagine the planet's outer layers sliding like loose skin around a misaligned core, gradually pulling the entire world off kilter. If true, Uranus could be the solar system's most dramatic example of planetary self-sabotage, a world that literally turned itself sideways from the inside out. Every probe that's ever flown past Uranus, Voyager 2 in 1986, for instance, has raised more questions than answers. Without a dedicated mission to map its interior and measure its wobbles, we're left with theories as tilted as the planet itself. Whether shattered by ancient impacts or reshaped by unseen forces, Uranus stands as a cosmic oddball, a reminder that even the giants of our solar system have hidden histories written in the language of gravity and time. And until we go back, its sideways spin will remain one of the solar system's most stubborn enigmas, a puzzle literally billions of years in the making. Miranda is the solar system's jigsaw puzzle gone wrong, a moon that looks less like a world and more like a celestial Frankenstein, stitched together from mismatched pieces. Of all the moons orbiting Uranus, Miranda stands out as the strangest, its surface a chaotic patchwork of canyons, ridges, and cratered plains smashed together with no obvious logic. Some regions look like ancient, battered terrain, while others are smooth and young, as if ripped from another moon entirely, the most striking feature. Vast sheer cliffs like Verona Rupes, plunging 12 miles straight down the tallest known cliff in the solar system. If you jumped from the top, it would take you nearly 10 minutes to hit the bottom. How did Miranda end up looking like a shattered plate glued back together by a careless giant? The leading theory is as dramatic as the moon itself. Miranda might have been smashed apart and reassembled multiple times. In the early days of the solar system, when impacts were frequent, a massive collision could have shattered Miranda into fragments, only for gravity to pull those pieces back together in a haphazard order. Think of it like dropping a glass bowl. Once broken, you can glue it back together, but the cracks remain, and the pieces never quite align as they originally did. Miranda's jumbled terrain, especially the coronae odd, trapezoidal regions covered in grooves and ridges, could be the scars of these ancient cataclysms, where hot, soft material oozed up through cracks before freezing into new, deformed landscapes. But not everyone agrees. Some planetary scientists argue tidal forces from Uranus could have stretched and twisted Miranda's interior, creating enough heat to melt parts of its icy shell without shattering it entirely. This tectonic tango might explain why some regions appear stretched and folded like taffy, while others stayed rigid. Others suggest cryovolcanism, icy eruptions spewing slush instead of lava, could have resurfaced parts of the moon, smoothing over old scars with fresh, frozen flows. The problem: Miranda's gravity is so weak that any erupting slush would have likely sprayed into space rather than pooling neatly on the surface. The most tantalizing clue might lie in Miranda's orbit. Like many of Uranus's moons, it's locked in a gravitational dance with its neighbors, particularly Umbriel and Ariel. Over billions of years, these interactions could have yanked Miranda into eccentric, unstable orbits, triggering internal heating that melted and fractured its interior. If true, Miranda's bizarre surface might be the result of a slow-motion demolition, where gravity did the work of an asteroid, pulling the moon apart from the inside out. What makes Miranda truly special is that it's not just a relic, it might still be evolving. If tidal forces are active today, future missions could catch the moon in the act of reshaping itself, offering a front-row seat to the kind of geological violence that once shaped our own moon and Earth. For now, Miranda remains a cosmic riddle, a world where the usual rules of geology seem to have been thrown out the window, whether shattered by impacts needed by tides or reshaped by unseen forces. Its jumbled face is a testament to one thing: the universe has a flair for turning destruction into art. Neptune shouldn't be this hot. Floating 30 times farther from the sun than Earth, this ice giant receives only 1/900th of the sunlight that bathes our planet, yet somehow, it radiates 2.6 times more energy than it absorbs. That's like a freezer burning your hand when you open it. Uranus, nearly Neptune's twin in size and composition, barely emits any excess heat at all. So why is Neptune practically simmering with internal fury? The answer might lie in buried treasure, rain made of diamonds, or echoes of a violent birth that still rumbles beneath its azure clouds. At first glance, the explanation seems simple: leftover heat from the planet's formation 4.5 billion years ago. When gas and dust collapsed to form Neptune, gravitational energy converted into heat, much like how a bicycle pump warms up when you compress air. But that heat should have dissipated into space long ago unless something trapped it. That's where Neptune's exotic interior comes into play. Beneath those swirling blue methane clouds, pressures reach mind-bending extremes millions of times stronger than Earth's atmosphere. Here, methane molecules break apart, releasing carbon atoms that get crushed into crystalline structures. In other words, it rains diamonds. These diamond hailstones aren't just glittery curiosities, they're heat engines. As carbon crystals form and sink toward the core, they release gravitational energy, creating friction that warms the surrounding hydrogen and helium soup. Some researchers estimate this diamond rain could generate thousands of times more energy than Earth's entire geothermal output, but here's the catch: this process should also be happening inside Uranus, which shares similar chemistry. Why isn't it equally toasty? That's where the plot thickens. Neptune might be compensating for its sluggish start. Unlike Uranus, which was likely walloped by a colossal impact that left it thermally stunted, Neptune could have retained more primordial heat simply by cooling more slowly. Its storms, like the famous Great Dark Spot, act as atmospheric vents, releasing pent-up energy in raging whirlwinds. There's also speculation that Neptune's interior layers convect differently, with heavy elements like oxygen and nitrogen acting as insulators, trapping heat like a cosmic thermos. Yet the wildest theory involves a hidden layer of exotic matter. At the core, where temperatures hit 7,000 degrees, hydrogen might exist as a supersonic fluid, a bizarre state where protons move freely while electrons stay locked in place. This could create electric currents that generate additional heat, like a planetary-scale battery short-circuiting itself. Whatever the cause, Neptune's surplus energy has real consequences. It fuels the fastest winds in the solar system, howling at 1,300 miles per hour, and drives the mysterious jet streams that carve its cloud tops into intricate patterns. The deeper mystery isn't just where Neptune's heat comes from, it's why Uranus, so similar in so many ways, lacks it. Was Uranus's core permanently damaged by an ancient collision? Does Neptune have a secret radioactive element stash? Or is diamond rain just one piece of a much stranger puzzle? Until we send a probe to plunge through those sapphire skies, these questions will keep simmering, as unresolved as the planet's own restless energy. One thing's certain: in the outer solar system, even ice can burn. Triton doesn't play by the rules. While every other major moon in the solar system orbits its planet in a sedate, orderly fashion, moving in the same direction as the planet spins, Neptune's largest moon does the exact opposite. Triton races backward in a reversed or retrograde orbit, as if defying gravity itself. This cosmic rebellion isn't just a quirk, it's a smoking gun. Triton doesn't belong here. It was stolen, and the aftermath of that celestial heist left scars still visible today. Most moons form alongside their planets, born from the same swirling disk of gas and dust. But Triton's backward spin suggests a far more violent origin. This icy world, slightly smaller than Earth's moon, likely began its life in the Kuiper belt, the ring of frozen debris beyond Neptune where Pluto and its kin reside. Somewhere along the way, Neptune's gravity reached out and snatched Triton from its original path, forcing it into captivity. The mechanics of this cosmic kidnapping are staggering to imagine. For a planet to capture a moon as large as Triton, conditions had to be just right, perhaps a close encounter with a binary Kuiper belt object, where Neptune's gravity ripped the pair apart, keeping one as a trophy. The capture would have been catastrophic. Triton didn't settle gently into orbit. It was wrenched into place by unimaginable forces, leaving the entire Neptunian system in chaos. The heat generated by this event would have melted Triton's interior, explaining its youthful, resurfaced terrain, a patchwork of cantaloupe-like ridges and smooth plains forged by cryovulcanos erupting slushy nitrogen. But the violence didn't stop there. Neptune's original moon system, if it had one, would have been obliterated. Triton's arrival likely sent smaller moons careening into the planet or hurtling into space, clearing the stage for its solo performance. Today, Neptune's other moons are tiny compared to Triton, suggesting they formed later from the debris left behind, yet the most unsettling clue lies beneath Triton's frozen crust. Voyager 2 detected geysers spewing nitrogen gas 8 kilometers into space, proof that this captured world remains geologically active, that heat shouldn't last billions of years unless something is replenishing it. The answer might lie in tidal forces. Triton's orbit isn't just backward, it's also tilted, creating rhythmic tugs from Neptune that flex the moon's interior like a cosmic stress ball. This ongoing squeeze could be powering those eruptions, turning Triton into a pressure cooker with no release valve. What's truly eerie is Triton's fate. That same tug of war is slowly dragging the moon closer to Neptune. In a few hundred million years, it'll pass the Roche limit, the point where planetary gravity overcomes an object's structural integrity. When that happens, Triton will be torn apart, transforming into a dazzling ring system that might one day rival Saturn's. Until then, this backward moon serves as both a reminder of the solar system's violent past and a preview of its ever-changing future, a cosmic interloper whose defiance of the rules will eventually be its undoing. Pluto's heart isn't just a sentimental feature, it's a planetary engine. Stretching over 1,000 miles wide, this bright heart-shaped plain named Tombaugh Regio dominates the dwarf planet's surface, with its western lobe, Sputnik Planitia, acting as a colossal nitrogen glacier that pulses like a slow, frozen heartbeat. When New Horizons zipped past in 2015, it revealed a landscape unlike anything else in the solar system, a vast, churning sheet of solid nitrogen, cracked into polygonal cells that rise and fall like a cosmic lava lamp. But how does a world so far from the Sun, where temperatures hover near -400 degrees Fahrenheit, manage to sustain geologic activity at all? The answer lies in the delicate dance between ice, sunlight, and Pluto's wispy atmosphere. Sputnik Planitia isn't just sitting there, it's actively recycling itself. Nitrogen ice, soft and malleable even in Pluto's bitter cold, flows in slow-motion glaciers, creeping across the basin at speeds of a few centimeters per year. Sunlight, faint as it is, provides just enough energy to vaporize some of this nitrogen, lifting it into the atmosphere as gas. Meanwhile, in colder, higher elevations, that same gas condenses back into ice and snows down, completing the cycle. This creates a global conveyor belt of nitrogen, with Sputnik Planitia acting as the drain, always collecting fresh ice, which then oozes outward to feed smaller glaciers across Pluto's surface. The real magic happens beneath the ice. Scientists believe Sputnik's basin might hide a subsurface ocean, kept sloshy by heat from radioactive decay in Pluto's core. If true, this buried sea could subtly tilt the entire glacier over time, explaining why the heart always faces Pluto's largest moon, Charon, a cosmic game of gravitational tug-of-war between the two worlds. Even stranger, this icy heartbeat powers Pluto's winds. As nitrogen sublimates from Sputnik's sunlit side, it creates a thin but detectable breeze, pushing against the dwarf planet's rotation and sculpting its weather patterns. You wouldn't feel it on your skin. Pluto's atmosphere is 100,000 times thinner than Earth's, but over millennia, these whisper-thin winds have carved dark streaks into distant highlands, leaving behind evidence of their silent force. What's most astonishing is how alive this frozen heart makes Pluto seem. Most expected New Horizons to find a static, cratered relic, a fossil from the solar system's infancy. Instead, it revealed a world where ice dances, where landscapes renew themselves, and where even a dwarf planet billions of miles from the Sun refuses to sit still. Whether it's the shifting glaciers, the possible hidden ocean, or the atmospheric whispers they create, Pluto's heart isn't just a landmark, it's proof that even in the darkest, coldest corners of space, there's no such thing as dead ground. Beyond Neptune's orbit lies a cosmic frontier where the familiar rules of our solar system seem to break down. The Kuiper Belt, a vast ring of icy debris left over from the planet's formation. But out here, astronomers have stumbled upon something peculiar, a sharp, unexplained boundary where the number of objects suddenly plummets, as if someone built an invisible wall in space. This drop-off begins roughly 4.5 billion miles from the Sun, far beyond Pluto, and it defies everything we'd expect from a natural debris field. So what's blocking the Kuiper belt's outskirts? The answer might rewrite our understanding of the solar system's edges. One leading explanation points to a hidden disruptor, an unseen planet lurking in the darkness. Dubbed Planet 9 by researchers, this hypothetical world could be 10 times Earth's mass, orbiting so far out that it takes 10 to 20,000 years to complete a single trip around the Sun. Its gravity, the theory goes, would act like a cosmic broom, sweeping away or ejecting objects that venture too close, leaving behind the stark emptiness we observe. The evidence: a handful of distant Kuiper belt objects share bizarre, clustered orbits that tilt in the same direction, as if something massive herded them into alignment. But here's the catch: no one's actually seen Planet 9 yet. Its existence is inferred, a ghostly presence revealed only by its gravitational fingerprints. Not everyone's convinced. Some argue primordial conditions could explain the wall without invoking a new planet. In the solar system's infancy, drag from swirling gas and dust might have stunted the growth of objects beyond a certain distance, leaving the outer Kuiper belt sparse. Others propose that a close stellar flyby, a passing star in the Sun's birth cluster, could have ripped away the outer debris billions of years ago. There's even a wilder idea: the wall marks the edge of the Sun's gravitational influence, where the weak pull of nearby stars begins to dominate, stealing material into interstellar space. The stakes are higher than just a missing planet. If the wall is artificial, shaped by a hidden world, it means our solar system is far larger and weirder than we imagined. But if it's natural, it could reveal secrets about how planetary systems form and evolve. Future telescopes like the Vera Rubin Observatory might settle the debate, scanning the skies for Planet 9 or mapping the Kuiper belt's fringe in unprecedented detail. Until then, this invisible barrier remains one of astronomy's most tantalizing puzzles, a silent sentinel guarding the frontier between the known and the unexplored. In October 2017, astronomers spotted something unprecedented: a strange, cigar-shaped object hurtling through our solar system at nearly 200,000 miles per hour. Named Oumuamua, Hawaiian for scout, it was the first known visitor from interstellar space. But what made this cosmic traveler truly baffling wasn't just its origin, it was the way it moved. As Oumuamua raced away from the Sun, it did something no ordinary asteroid or comet should do: it accelerated without explanation, as if pushed by an invisible hand. At first, scientists assumed the acceleration was caused by outgassing, the same process that gives comets their tails. When sunlight warms a comet's icy surface, trapped gases erupt, creating jets that act like natural thrusters. But here's the problem: Oumuamua showed no visible signs of outgassing, no tail, no coma, no dusty envelope. Telescopes scoured every wavelength and found nothing. If gas was propelling it, why couldn't we see it? Some researchers propose the object might be made of pure hydrogen ice, which evaporates without leaving a trace. Others suggested it could be a chunk of nitrogen ice, like those found on Pluto, except no one's ever seen a nitrogen iceberg drifting between stars. Then came the wilder theories. Harvard astrophysicist Avi Loeb famously suggested Oumuamua might be artificial, a light sail fragment from an alien civilization, using sunlight pressure for propulsion. The math almost fits. Its flattened shape and unusual brightness variations match what we'd expect from a thin, reflective sail, but critics point out the odds. For humanity's first confirmed interstellar visitor to be alien tech stretches coincidence to breaking point. Perhaps the most intriguing clue lies in Oumuamua's spin. Unlike tumbling asteroids, it rotated predictably, yet its motion wobbled slightly, as if its shape was uneven. Could it be a splintered shard from a planet shattered by tidal forces? Or a fractal-like dust bunny, formed in the debris disk of a dying star, we may never know for sure. By the time we spotted Oumuamua, it was already racing out of reach, leaving behind only whispers of data and a trail of unanswered questions. What's clear is this: Oumuamua defies easy categorization. It's a cosmic Rorschach test, revealing more about our assumptions than its own nature. Future telescopes like the Vera Rubin Observatory might spot more of these interstellar interlopers, helping us discern whether they're natural oddities or something far stranger. Until then, Oumuamua remains a tantalizing enigma, a fleeting glimpse of the mysteries lurking in the dark between stars. Ceres, the largest object in the asteroid belt, hides one of the solar system's most mesmerizing mysteries, a cluster of radiant spots gleaming from the depths of Alcator crater like cosmic beacons. First spotted by NASA Dawn spacecraft in 2015, these dazzling patches reflect sunlight with an intensity that makes them stand out starkly against Ceres's otherwise dull, charcoal-colored surface. At first glance, they look like patches of snow, but Ceres is too warm for ice to survive exposed in most places, so what's creating these bright anomalies? The answer could reshape how we view dwarf planets and the potential for hidden activity in the most unexpected places. Close-up observations revealed the spots are made of sodium carbonate, a shiny salt mineral commonly found in Earth's hydrothermal environments. But here's the twist: these deposits aren't just sprinkled on the surface, they're piled into domes and mounds, suggesting they weren't left behind by a one-time event. The brightest patch, Cerealia facula, sits at the center of Alcator crater and appears to be the product of ongoing, possibly recent, geologic activity. Some scientists believe a reservoir of briny water lurks beneath the crater, occasionally pushing mineral-rich sludge up through fractures in the crust. When this slurry reaches the surface, water evaporates into the near vacuum of space, leaving behind the gleaming salt deposits we see today. Not everyone agrees. An alternative theory suggests the spots could be remnants of cryovolcanism, eruptions of icy magma, instead of molten rock. Ceres's interior might still hold pockets of ammonia-rich water, kept liquid by residual heat from radioactive decay. When impacts like the one that formed Alcator crater shattered the surface, this buried slush could have oozed out, creating salt-laced frozen fountains. The dome-like structures might then be cryovolcanic vents, their shapes sculpted by repeated eruptions over millions of years. The implications go far beyond Ceres. If a small, seemingly inert world like this can harbor briny reservoirs or even occasional cryovolcanic activity, where else might we find similar surprises? Jupiter's moon Europa and Saturn's Enceladus have stolen the spotlight for their subsurface oceans, but Ceres proves even objects without a giant planet's tidal heating can stay geologically lively. Its bright spots hint at a hidden network of liquid pockets, possibly connected by deep fractures, a subterranean plumbing system that occasionally leaks its contents into the sunlight. The real enigma is timing. Some of these deposits appear startlingly fresh, with little discoloration from space weathering. That raises a tantalizing question: could Ceres still be active today? Dawn's data detected traces of water vapor near Alcator crater, like faint breaths escaping into space. Whether from lingering subsurface eruptions or slow seepage of brines, the possibility that this dwarf planet isn't quite dead keeps scientists riveted. Ceres's glowing spots are more than just a curiosity, they're a testament to the solar system's hidden vitality. In a realm once written off as frozen and static, these shimmering patches whisper of unseen forces at work, of salt and water and heat conspiring beneath the surface. And until we send another mission to peer closer, their brilliance will remain both a beacon and a riddle, reminding us that even in the asteroid belt's quiet corners, the universe refuses to sit still. On the night of August 15, 1977, a radio telescope in Ohio captured something extraordinary, a 72-second burst of sound so powerful that an astronomer famously scrawled, "Wow." In the margins of the data printout, this signal, blasting from the constellation Sagittarius at a frequency hydrogen atoms naturally emit, remains one of the most tantalizing hints that we might not be alone in the universe. But here's the haunting part: despite decades of searching, the WOW signal never repeated. Was it a fleeting cosmic coincidence, or did we intercept a message that slipped through our fingers before we could reply? The signal's sheer intensity sets it apart. The Big Ear telescope at Ohio State University recorded it at 30 times louder than background noise, a spike so sharp it couldn't be dismissed as stellar static. Its frequency, 1420 MHz, sits in a protected, quiet zone where earthly broadcasts are banned to avoid interference. That made it the perfect channel for extraterrestrial communication, a universal "we're here" etched onto a wavelength any civilization studying hydrogen would recognize. Yet no known natural phenomenon, pulsars, quasars, or comets matches its profile. Even Jupiter's magnetosphere, a notorious radio screamer, couldn't produce something so focused and brief. Skeptics argue it might have been a reflected human signal, bouncing off space debris or a passing satellite. But here's the flaw: our broadcasts rarely stay so precisely tuned to one frequency, and no military or civilian transmission from 1977 fits the bill. Others suggest a rogue asteroid or interstellar object, like Oumuamua, could have briefly acted as a cosmic mirror, focusing distant radio waves toward Earth. The problem: nothing's ever been found along that line of sight to explain it. Then there's the chilling possibility it was intentional. If an alien civilization aimed a directional beacon our way, the signal would sweep past Earth like a lighthouse beam, explaining why we caught it once and never again. Modern SETI projects like Breakthrough Listen now scan thousands of stars simultaneously, hoping to catch another wow moment. But the original signal's ephemeral nature raises a darker question: what if we're not listening the right way? Most searches assume extraterrestrials will broadcast continuously, but what if their messages are sporadic, or worse, what if they've already moved on? The WOW signal endures as a cosmic Rorschach test. To some, it's proof we're on the right track; to others, a cautionary tale about reading too much into noise. What's undeniable is how it reshaped our search for intelligence beyond Earth. Every new telescope, every algorithm sifting through radio static, carries its legacy, a reminder that the universe might be shouting, but we're still learning how to listen. Most stars flicker predictably, their light curves tracing gentle dips as planets glide past. Then there's Tabby's star KZ84628522, a cosmic rebel that dims erratically, sometimes plunging by 20% for days or weeks before flickering back to normal. Discovered in 2015 by citizen scientists combing Kepler Space Telescope data, this star's bizarre behavior defies all textbook explanations. Forget tidy planetary transits, Tabby's star drops its brightness like a malfunctioning bulb, leaving astronomers scrambling for answers. What's blocking its light? The theories range from cosmic dust to something far more provocative: alien megastructures. At first glance, the megastructure hypothesis seems ripped from science fiction. The idea an advanced civilization could be building a Dyson swarm, a colossal array of solar collectors encircling the star to harness its energy. These hypothetical constructs, first proposed by physicist Freeman Dyson, would partially obscure the star's light in irregular patterns, much like what we observe. The allure of this explanation lies in the star's unique fingerprint. No natural phenomenon we know of causes such drastic, aperiodic dimming. But before we hail our extraterrestrial neighbors, there's a catch. Alien megastructures would emit waste heat as infrared radiation, and follow-up observations found no excess infrared signals around Tabby's star. That's where the dust cloud theory comes in. Detailed spectral analysis revealed the dimming events affect blue light more than red, a telltale sign of fine particles scattering shorter wavelengths, just like Earth's atmosphere makes the sky appear blue. The culprit might be vast swarms of comet fragments or circumstellar debris, kicked up by a recent planetary collision or a family of exocomets orbiting too close. These dusty clouds could explain the star's long-term fading. 2. Archival data shows Tabby's star has dimmed by 14% over the past century. Still, even this tidy explanation has holes. Why would dust block so much light without leaving clearer spectral fingerprints, and how could comets generate such extreme, uneven dimming? Then there's the stellar oddball angle. Tabby's star might be a rare type of variable star, one that undergoes internal convulsions we've never witnessed before. Some researchers suggest magnetic activity or spot cycles far more violent than our sun's could warp its light output. Others propose it recently devoured a planet, causing temporary bloating and dimming as it digests the remains. The challenge: no known stellar behavior matches both the sudden dips and the century-long decline. The truth might lie in a combination of factors, a cosmic perfect storm. Imagine a young, dusty system with swarms of comets, a faint debris disk, and a star prone to fits of magnetic rage. Together, these elements could choreograph a light show just erratic enough to defy simple categorization. Or perhaps the answer is something entirely new, a phenomenon we haven't yet imagined. Tabby's star remains a riddle wrapped in a mystery, its secrets hiding in plain sight. Whether the solution points to alien engineering or undiscovered astrophysics, one thing's clear: the universe keeps inventing puzzles we're only beginning to comprehend. And until we train more telescopes on this stellar enigma, its flickers will continue to taunt us, silent, cryptic, and utterly irresistible. The Pioneer spacecraft should have been coasting smoothly through the void, their trajectories etched into the equations of celestial mechanics with Newtonian precision. But something was off. As scientists tracked Pioneer 10 and 11, two of humanity's first emissaries to the outer solar system, they noticed an unsettling discrepancy. Both probes were slowing down, not from the drag of solar wind or interstellar dust, but as if an invisible hand were tugging them backward toward the sun. This drift was tiny, just 300 miles per decade, but in the frictionless realm of space, even microscopic deviations defy explanation. Dubbed the Pioneer anomaly, this mystery became one of the most stubborn puzzles in modern astrophysics, sparking debates that stretched from the mundane to the revolutionary. At first, engineers suspected mundane causes: gas leaks from thruster systems, or uneven heat radiating from the probe's plutonium power sources. Pioneer's design made it a prime candidate for thermal mischief. Unlike later missions which use thrusters oriented to cancel out recoil, Pioneer's heat vented asymmetrically, primarily from its rear. Photons carrying that warmth would exert a minuscule push, a photon recoil force like sparks from a rocket nudging it off course. When researchers crunched the numbers, thermal radiation did account for some of the anomaly, but not all. Even after meticulous modeling, roughly 10% of the deceleration remained unaccounted for. Could the answer lie in overlooked engineering quirks, like infrared emissions from electrical wiring, or was something far stranger at play? That's when the theorists stepped in. If conventional physics couldn't explain the anomaly, perhaps the laws themselves needed revisiting. Some proposed modifications to Einstein's general relativity, suggesting gravity might behave differently at the solar system's edge. One radical idea invoked modified inertia, where the fabric of spacetime itself resists acceleration in ways we don't yet understand. Others floated dark matter, invisible particles clustered near the sun, tugging on the probes, though no other spacecraft exhibited similar behavior. The most tantalizing and controversial hypothesis: a flaw in our understanding of gravity's inverse square law, hinting at hidden dimensions or unknown forces governing cosmic motion. The debate raged until 2012, when a team of researchers performed a forensic reconstruction of Pioneer's heat emissions using decades-old telemetry and modern supercomputers. Their conclusion: Thermal radiation could explain the entire anomaly if you accounted for every last watt of heat radiating from every bolt, panel, and antenna. The lingering discrepancy vanished when they factored in warmth bouncing between the spacecraft's components, a subtlety earlier models had missed. Case closed. Not entirely. Some scientists still argue the thermal explanation leaves gaps, and without fresh data from identical deep space probes, the anomaly retains a whisper of mystery. What makes the Pioneer anomaly so compelling isn't just the science, it's the lesson hidden in its resolution. Even in the razor-sharp world of physics, the universe thrives on ambiguity. A flaw in our models, a missed variable, and suddenly the cosmos seems to bend its own rules. Whether the culprit was heat or something more profound, Pioneer's ghostly deceleration reminds us that every answer uncovers new questions, and sometimes the greatest discoveries begin with a drift in the dark. The moon's gravity should be smooth, a gentle, uniform pull shaped by its spherical mass, but when Apollo astronauts orbited overhead, their spacecraft wobbled unpredictably, tugged by invisible forces beneath the surface. These weren't random fluctuations. Hidden beneath the lunar crust lay monstrous scars from ancient violence, mass concentrations, or maskins, distorting gravity like cosmic speed bumps. Their discovery rewrote our understanding of the moon's battered history, revealing an alien landscape where gravity itself is warped by catastrophe. Maskins aren't just subtle anomalies, they're gravitational bullseyes, often stronger than Earth's pull in spots. Picture a buried cannonball the size of a mountain range, lurching satellites into erratic orbits. The first clues came in the 1960s, when NASA lunar orbiter missions struggled to stay on course. Scientists expected minor variations, but the data showed sharp spikes centered over circular basins like Mare Imbrium and Mare Serenitatis, colossal impact sites filled with dark volcanic plains. The correlation was undeniable. These regions held excess mass, as if gargantuan iron-rich asteroids still lay entombed beneath the lava. How did such dense pockets form? The leading theory paints a violent past. Billions of years ago, during the late heavy bombardment, asteroids as wide as cities pummeled the moon, excavating basins hundreds of miles wide. The impacts didn't just leave craters, they shattered the lunar mantle, allowing denser material from deep below to rebound upward. Later, volcanic floods of basalt lava seeped in, pooling over the disrupted terrain like syrup over a cracked plate. The result, a layered bullseye, heavy mantle material beneath, topped by even denser lava, creating a gravitational fingerprint far denser than the surrounding crust. But maskins aren't just relics, they're active troublemakers. Modern orbiters like NASA Grail mission have mapped their fingerprints in exquisite detail, revealing how their uneven pull drags spacecraft lower over time. Without constant course corrections, lunar probes would eventually spiral into the dust. This bizarre behavior even affects future missions. Landing near a maskin requires extra fuel to counteract its invisible grip. Some maskins exert so much force that they visibly warp the moon's crust, creating wrinkles and ridges visible from orbit. The oddest twist, maskins might be time capsules. Their unique signatures allow scientists to date the basins they inhabit. Older impacts have more relaxed gravitational profiles, their mass concentrations spread outward by eons of slow lunar adjustments. Younger basins like the billion-year-old Orientale still cling to their original dense cores, their violence frozen in gravitational amber. By studying these anomalies, we're not just decoding the moon's trauma, we're piecing together the solar system's most chaotic era, one buried scar at a time. Yet mysteries linger. Some maskins don't align neatly with visible basins, hinting at hidden impacts buried under later lava flows. Others show gravitational donuts, rings of excess mass with unexplained hollow centers. Could these be signatures of double impacts, or did the moon's molten past sculpt even stranger subterranean geometries? Each unanswered question peels back another layer. proving that even in something as fundamental as gravity, the cosmos thrives on surprise. The moon's lumpy pull isn't just a scientific curiosity, it's a testament to the violence that shaped our celestial backyard, written in a language of invisible tides. The sun's core is a nuclear furnace, fusing hydrogen into helium at a staggering rate, a process that should flood space with a predictable torrent of ghostly particles called neutrinos. But when scientists first tried to measure these solar neutrinos in the 1960s, their detectors came up short. Only a third of the expected neutrinos showed up, sparking a decades-long conundrum known as the solar neutrino problem. At first, researchers assumed their instruments were flawed, then they wondered if they misunderstood the sun itself. The truth turned out to be far stranger. Neutrinos were playing a cosmic shell game, shape-shifting en route to Earth in ways that defied the laws of physics as we knew them. Early neutrino detectors, like the Homestake experiment buried in a South Dakota gold mine, relied on chlorine tanks to catch these elusive particles. When a neutrino struck a chlorine atom, it transformed into radioactive argon, a telltale sign scientists could count. Problem was, Homestake detected only 27% of the neutrinos predicted by solar models. For years, the discrepancy haunted astrophysics. Was the sun's core cooler than we thought? Did neutrinos somehow vanish on their way to Earth? The breakthrough came from an unexpected direction: particle physics. Neutrinos, it turns out, come in three flavors: electron, muon, and tau, and they have a bizarre habit of oscillating between these identities as they travel. The sun produces only electron neutrinos, but by the time they reach Earth, many have morphed into muon or tau neutrinos, invisible to early detectors tuned solely for the electron variety. This revelation, confirmed by experiments like Japan's Super Kamiok and in the late 1990s, didn't just solve the solar neutrino puzzle, it proved neutrinos have mass, a fact that upended the standard model of particle physics. The implications ripple far beyond the sun. Neutrino oscillation means these particles, once thought weightless, must have some infinitesimal mass, a discovery that earned the 2015 Nobel Prize in Physics. It also hints at gaps in our understanding of quantum mechanics. Why do neutrinos oscillate at all? Could there be even more flavors, like sterile neutrinos, invisible to all known detectors? The answers might lie in next-generation experiments like DUNE, which will shoot neutrinos through 800 miles of Earth to study their transformations with unprecedented precision. What began as a solar mystery became a window into the subatomic realm, proving even the tiniest particles hold universe-altering secrets. The sun's missing neutrinos weren't missing at all, they were hiding in plain sight, masquerading as something else. And their cosmic game of disguise reminds us that sometimes, the most profound truths emerge not from what we observe, but from what we almost overlook. Look up at the night sky just before dawn or after dusk, and you might spot something haunting, a faint, triangular glow stretching upward from the horizon, along the path where the planets travel. This ethereal phenomenon, called the zodiacal light, has puzzled stargazers for centuries. It's not the Milky Way's soft haze or the glow of distant cities, it's sunlight reflecting off countless tiny particles drifting through the inner solar system. But where does this cosmic dust come from? The answer is far from settled, and the debate reveals just how chaotic our celestial neighborhood really is. For decades, scientists assumed comets were the primary culprits. These icy wanderers, often called dirty snowballs, shed dust as they near the sun, leaving behind trails of debris. When Earth plows through these trails, we get meteor showers, but over time, the dust spreads out, forming a diffuse cloud along the ecliptic plane. Observations seem to back this up. Studies in the 1990s linked the zodiacal dust to Jupiter family comets, whose orbits bring them close enough to the sun to steadily replenish the reservoir. But here's the catch: modern measurements reveal a mismatch. The dust particles in the zodiacal cloud are smaller, and more abundant than what most comets typically produce. If comets alone were responsible, we'd expect a different size distribution, with more chunky fragments mixed in. That's where asteroids enter the picture. The inner solar system is littered with these rocky bodies, and when they collide, which happens more often than you'd think, they grind each other to dust. High-resolution surveys have detected plumes of debris erupting from asteroid impacts, and some of this material could spiral inward over time, drawn by the sun's gravity. The Japanese Hayabusa mission even captured direct evidence of this process when it visited the asteroid Itokawa, finding its surface covered in fine grains ejected by micrometeorite strikes. Yet asteroids have their own inconsistencies. Most of their collisions occur in the main belt, between Mars and Jupiter, far from where the zodiacal light is brightest. How does so much of this dust migrate inward without dispersing into interstellar space? The plot thickens when you consider Mercury's role. Recent data from NASA Messenger probe revealed the tiny planet might be leaking dust into the zodiacal cloud. Mercury's surface is constantly bombarded by solar wind and micrometeorites, kicking up tiny particles that could get trapped in orbit around the Sun. Some researchers argue this mercurial dust might contribute more than we thought, especially since the planet's close proximity to the Sun means its debris would naturally align with the ecliptic plane. But modeling this process is tricky. Mercury's gravity is weak, and solar radiation should blow most of this dust away before it can accumulate. Then there's the wild card, interstellar interlopers. Missions like Stardust have caught particles from outside our solar system mixed into the zodiacal cloud, raising the possibility that some of this dust isn't homegrown at all. Could passing stars or molecular clouds dump foreign material into our system, adding to the glow? It's a tantalizing idea, but the amounts detected so far are too minuscule to explain the zodiacal light's intensity. What makes this mystery so compelling isn't just the question of origin, it's what the dust reveals about the solar system's invisible dynamics. These particles aren't static, they're part of a slow-motion ballet, spiraling toward the Sun over millennia in a process called Poynting-Robertson drag. Larger grains drift inward, while radiation pressure blows the smallest ones outward, creating a delicate equilibrium. The zodiacal light is essentially a cosmic fossil record, preserving clues about collisions, migrations, and even the Sun's ancient activity. Future missions like Europe's Comet Interceptor or NASA Interstellar Mapping and Acceleration Probe might finally settle the debate by analyzing dust composition in unprecedented detail. Until then, the zodiacal light remains a silent enigma, a shimmering veil of dust that's as beautiful as it is mysterious, reminding us that even the emptiest corners of space are anything but empty. Deep in the swirl of conspiracy theories, one story keeps resurfacing: the tale of the Black Knight satellite, a supposed 12,000-year-old alien probe silently orbiting Earth. Stories claim it transmits mysterious signals, appears in medieval tapestries, and was even photographed by NASA astronauts, but strip away the mythology, and what's left? The truth is a fascinating collision of Cold War secrecy, misidentified space debris, and human imagination running wild. The legend began in the 1950s when newspapers reported unusual radio echoes detected by astronomer Duncan Lunan. He suggested these delays might be reflections from an ancient object in high Earth orbit. Though Lunan later retracted his theory, the idea stuck: a phantom satellite watching us. Then came the grainy 1960s NASA images of an unidentified object during the Mercury missions, fueling claims of a government cover-up. But here's the reality: those photos almost certainly show thermal blankets or discarded spacecraft parts lost during early spacewalks. The Black Knight label, it was likely borrowed from a British science fiction serial about a sinister orbital device. Dive deeper, and timelines unravel. Proponents point to Nikola Tesla's 1991 account of intercepting peculiar radio signals as evidence of early contact, yet Tesla never described a satellite. He speculated about intelligent Martian communication. Similarly, the medieval sighting, often cited a strange shape in a 14th century painting, is just an artistic depiction of an eclipse, even the infamous 12,000-year age claim. It traces back to a misquoted Russian scientist discussing hypothetical extraterrestrial artifacts, not a real discovery. So where does the Black Knight myth persist? Blame orbital clutter. Earth's skies are littered with defunct satellites, rocket boosters, and other debris. Over 34,000 tracked objects as of 2024. Some, like the 1965 OG-01 satellite, re-enter the atmosphere in dramatic fireballs, sparking fresh UFO panics. Others, like the 2018 empty trunk from a secretive U.S. mission, become temporary celebrities before burning up. The Black Knight endures because space is messy and humanity loves a mystery. NASA official stance. No anomalous satellites exist, but the agency's transparency hasn't stopped the legend. Every discarded thermal panel or stray bolt becomes fodder for speculation when viewed through the lens of conspiracy. Perhaps the real lesson here isn't about aliens, it's about how easily artifacts of human spaceflight morph into cosmic folklore when left unexplained. And in an era of mega-constellations and space tourism, the next Black Knight is already waiting, hidden in plain sight among our own celestial junkyard. Before Einstein rewrote the rules of gravity, astronomers were convinced something was tugging at Mercury, an unseen force nudging its orbit in ways Newton's equations couldn't explain. The culprit, they assumed, had to be a hidden world lurking between Mercury and the Sun, a planet so close to the solar furnace it was nearly impossible to spot. They even gave it a name, Vulcan, after the Roman god of fire. For decades, respected scientists hunted this phantom world, publishing supposed sightings and calculating its orbit. But Vulcan wasn't just elusive, it was a mirage, a cosmic misunderstanding that would take relativity to unravel. The hunt began in 1859, when French mathematician Urbain Le Verrier, the same man who'd predicted Neptune's existence by studying Uranus's wobbles, turned his attention to Mercury's strange behavior. The planet's perihelion, its closest point to the Sun, shifted slightly faster than Newtonian physics allowed. Le Verrier's solution: an undiscovered planet's gravity must be perturbing Mercury's path. The idea wasn't far-fetched. Neptune's discovery had proven math could reveal invisible worlds. Almost immediately, amateur astronomer Edmond Modest Lescarbault claimed to spot Vulcan transiting the Sun, and Le Verrier celebrated the apparent confirmation. Soon, others reported similar sightings, despite the glaring problem: if Vulcan existed, it should have been obvious during total solar eclipses, when sunlight dimmed enough to reveal nearby objects. The contradictions piled up. Some observers described Vulcan as a faint dot racing across the solar disk, while others swore it was a blurry smudge. A few even mapped its orbit, convinced it revolved around the Sun every 19 days. But with each new discovery, the predicted positions failed to align. By the 1870s, skepticism grew. Eclipses came and went with no sign of Vulcan, and astronomers began questioning whether sunspots or instrument flaws had tricked their predecessors. Yet Mercury's orbital oddity remained, a stubborn enigma that refused to fade. The answer arrived in 1915, not from a telescope but from a chalkboard. Einstein's general theory of relativity revealed that Mercury's anomaly wasn't caused by a hidden planet, it was a side effect of the Sun's warped spacetime. In Einstein's universe, massive objects like the Sun bend the fabric of reality itself, altering the paths of nearby objects. Mercury, orbiting so close, experiences this curvature intensely, causing its perihelion to advance precisely as observed. No Vulcan needed. Relativity didn't just solve the mystery, It rendered the phantom planet obsolete overnight. Ironically, the Vulcan episode wasn't a total failure. It pushed astronomers to scrutinize Mercury's motion more closely, laying groundwork for the precise measurements that would later verify Einstein's theory. Today, Vulcan endures as a cautionary tale about human bias, a reminder that when our models fail, the solution isn't always another piece in the puzzle. Sometimes we need to redesign the puzzle entirely, and while no planet burns beside the Sun, the ghost of Vulcan lingers, a testament to the lengths we'll go to make the cosmos conform to our expectations until the cosmos teaches us to think differently. The universe is unimaginably vast, trillions of stars, countless planets, and yet, we've found no definitive proof of other civilizations. This contradiction is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the sheer number of potentially habitable worlds, the silence is deafening. Shouldn't the cosmos be buzzing with life? The answers we've come up with range from sobering to downright chilling. One explanation is the idea of great filters, barriers so formidable that almost no life surpasses them. These could be behind us, meaning Earth got impossibly lucky. Maybe complex life is extraordinarily rare, or self-destruction through war or climate collapse is inevitable for advanced civilizations, even more unsettling. The filter might still lie ahead. If technological species always hit a wall, whether from AI gone rogue, gamma-ray bursts, or some other existential threat, then our own future could be far bleaker than we imagine. Then there's the zoo hypothesis, the notion that advanced aliens know we're here but deliberately avoid contact, treating Earth like a cosmic wildlife preserve. It sounds like sci-fi, but consider humanity's own protocols for uncontacted tribes. If a civilization values non-interference, they might observe us from a distance until we reach a certain maturity. But if that's true, why no probes, no subtle signals? The silence feels less like patience and more like indifference. Another possibility is that we're simply alone. The conditions for life might be so precise: planet type, star stability, moon-induced tides, even galactic location, that we're the first or the only ones. Or perhaps intelligence like ours is an evolutionary fluke, a brief spark in an otherwise lifeless void. Yet there's a wilder take: we're looking for the wrong things. Alien civilizations might communicate through neutrinos or quantum entanglement, technologies we can't yet detect, or they've transcended physical forms, existing as digital entities in Dyson swarms, invisible to our telescopes. The Fermi paradox isn't just about aliens, it's a mirror. Every possible solution forces us to confront humanity's fragility, our future, and whether we'll ever hear a voice answering back from the dark. Until then, the question lingers, haunting our search for answers among the stars. Could our sun have a dark companion, a hidden star whose periodic visits unleash catastrophe on Earth? This is the chilling premise of the Nemesis star theory, a hypothesis proposing that a distant, unseen object orbits our solar system every 26 million years, triggering mass extinctions by hurling comets toward the inner planets. The idea emerged in the 1980s when paleontologists noticed a grim pattern in Earth's fossil record. Life seems to collapse in regular intervals, with 5 major extinction events spaced roughly 26 to 30 million years apart. Coincidence? Some scientists think not. The mechanics of Nemesis are as elegant as they are terrifying. If a dim, cool star, likely a red dwarf or brown dwarf, circled the Sun in a vast, elliptical orbit, its gravitational pull could disturb the Oort cloud, a reservoir of icy bodies at the solar system's fringe. Each time Nemesis swings closest to the Sun, it would send a hail of comets careening inward, some of which might strike Earth. The evidence isn't purely speculative. The Cretaceous-Paleogene extinction, which wiped out the dinosaurs 66 million years ago, was triggered by an asteroid or comet impact. So too was the Triassic-Jurassic event, 200 million years ago. Even the geologic record shows peaks and impact craters coinciding with die-offs, yet for all its narrative power, Nemesis remains a theory without proof. Modern sky surveys like WISE Wide Field Infrared Survey Explorer have scoured the cosmic neighborhood for cold, faint stars and turned up empty. If Nemesis exists, it should have been spotted by now unless it's a rogue planet or an exceptionally stealthy brown dwarf. There's also the timing problem. As researchers refined Earth's extinction timeline, the perfect 26 million year cycle began to look less precise, with some events clustering and others drifting out of sync. Critics argue that random asteroid strikes and volcanic activity could explain the patterns without invoking a stellar Grim Reaper. Perhaps the most compelling counterpoint comes from astronomy itself. Binary star systems are common, but most companions orbit much closer than Nemesis would need to. A star lingering trillions of miles away would be weakly bound to the Sun, vulnerable to disruption by passing stars or galactic tides. Simulations suggest such a distant pairing would rarely survive the Milky Way's chaotic environment for billions of years. Still, the allure of Nemesis persists. It's a reminder of how fragile life is, how a single unseen force could rewrite Earth's history in an instant, and while the Death Star may remain hypothetical, the search for hidden solar companions goes on. New telescopes like the upcoming Vera Rubin Observatory might finally settle the debate, scanning the skies for whispers of movement in the dark. Until then, Nemesis lingers at the edge of our imagination, a ghostly specter of cosmic vengeance, or perhaps just a cautionary tale about finding patterns where none exist. Either way, the theory challenges us to look deeper, to question not just what we see, but what might be lurking just beyond the light. From the icy heart of Pluto to the hexagonal storms of Saturn, from Mercury's impossible frost to Neptune's diamond rain, we've journeyed through 30 of the solar system's most tantalizing unsolved mysteries. Each one is a reminder that the cosmos thrives on questions, defying expectations, overturning old assumptions, and proving that the more we explore, the less we truly know. These puzzles aren't just scientific curiosities, they're invitations to look deeper, to wonder boldly, and to keep pushing the boundaries of what's possible. Think about the courage it takes to send probes into the unknown, to build telescopes that peer back in time, to stare into the void and say, "Tell me your secrets." Every mystery we've uncovered, whether it's the missing mass of Jupiter's core or the eerie silence of the Fermi paradox, is a testament to humanity's restless curiosity. These aren't dead ends, they're stepping stones. The Great Red Spot's endurance teaches us about chaos and order. The face on Mars reminds us of the stories we project onto the stars. Europa's hidden ocean whispers that life might flourish in the unlikeliest places. But here's the beautiful part: these mysteries belong to all of us. You don't need a PhD to marvel at Saturn's disappearing rings, or to ponder why Venus turned into a hellscape while Earth flourished. The universe doesn't discriminate, it dangles its enigmas in front of anyone willing to look up and ask, why? So tell us, which mystery captivates you? Is it the phantom pull of Planet 9, the riddle of Oumuamua's acceleration, or something else entirely? Drop your favorite in the comments, because the conversation doesn't end here. The greatest lesson of these 30 puzzles: humility. For all our knowledge, we've barely scratched the surface. There are worlds where storms rage for centuries, moons with hidden oceans, and forces we can't yet name shaping the fabric of reality itself. And that's exhilarating. It means there's always more to discover, always another layer to peel back. So keep wondering, keep questioning, and most of all, stay hungry for the next great cosmic revelation, because as long as the stars shine, the universe will keep surprising us. The adventure is just beginning.